All right. Hello, everyone. Sorry, I was a little bit late. How's your weekend? Good. Why do you sit there? You always sit there. All right. So I'm grading your exams. I'm halfway through. So some of you got your grade. I'll bring them on Wednesday. So I'll finish everyone. So the trick, if you pick trick, you'll get 2 points on question 1. If you pick treat, you get 2 points overall. Doesn't matter where you need it. So trick part was your on question 1. You're right. You did right choice. If you forgot, you're lost. If you didn't write it, a couple of you didn't write it, so you didn't get any point. So, okay, on Wednesday, I have a meeting in the college, so I can only be in my office hours for half an hour, 11 to 11:30. So I'll be on Zoom and in person, but I have to go right away, and then I won't be back to the building until later in the afternoon. So if you need my help on programming, just give you ideas, not to help, like check over your code. You can also send me an email. All right, help each other on Discord, but keep it where I can see how you're helping each other. Right? Okay. Today we will have our last piece on dynamic. Then we will move on to control. Right? But then since we have different backgrounds in the class, I'm gonna review control a little bit. So the first 2 lecture on control is review, and you might know already a lot about it, but then after that there will be new stuff. Okay, I need to check how many classes we have left to see how much I'm going to teach. So I might change my plan a little bit based on what I think is more important for you. All right, sounds good? So if you didn't finish today's lecture until the end, we'll pick up on Wednesday. I'll review control on Wednesday. Friday, there's no classes, and you come back next Monday, and then you're basically going to join control. Yes, it's more fun. Okay. But I think it's fun. I don't know. My definition of fun is very different, so I don't know. Has been different for a while. Okay, you need to see this. I'm recording. Okay, so we will go over the explicit form of Lagrange. So whatever you learn about Lagrange, the equation and everything stays the same. The way that we derive the equation, there's another option to do it, explicit form. Do you remember that we spent so much time on learning Jacobians? I'm going to use it here. If you know the Jacobians, the linear and J omega and JB and J omega, angular, you can write the equation of motion as well. So it is very important to find Jacobian, right? So you remember the form of the Lagrange equation? Well, that's the equation of motion. So Lagrange is L equal to K minus U, right? Kinetic energy minus potential energy. This is when we write the equation of motion based on, so this is Lagrange Euler-Lagrange equation. When I say this, I mean this. Now we are using forced because we have external force and torques. You might see Lagrange in Euler-Lagrange equation equal to 0. There's no external force for that. So we are considering force though, because we have actuators, so we obviously have force and torques. We said G is a gravitation. So for us, it's potential energy. The only one we deal with is the gravitational, right? So and then you find a partial derivative of that with respect to your joint variables for that. When we are talking about the kinetics, we are finding the partial differential of our kinetic energy with respect to joint variable, the rate of change of joint variable or the velocities, and also joint variables. So Q and Q dot. So Q is your general generalized variables. So it could be theta, it could be d, we just call it q. All right, this is all just review from last week. Now, if you remember, our kinetic energy could be because of linear velocity and angular velocity. If we can write it in generalized form, we can write it like this. We can say that kinetic energy is 1/2 q dot transpose some matrix in the middle, right? Call it m, times q dot. Now, since these are generalized, could be omega, it could be theta dot, right? Or d dot. If we write it that way and we get all the, and we put them back here, we are going to, I'm missing it. We are going to perform each of those partial differential and see what happens. So, partial differential of k with respect to q dot, if our k is defined as such, then if you get the partial differential with respect to that, you're gonna get some mq times q dot, because that one comes out and then gets canceled. If you get the derivative of that with respect to time, you will have to get the derivative of m, and they get the derivative of q dot. So you can say m q double dot plus, so this is the chain rule, m dot q dot. M dot, if you remember, is inspired, right? So now this would be the equivalent of this expression in that equation. Now, if we deduct this from, we get the partial differential of that with respect to q, we get something like this. So this is the mq double dot part. I'm changing the color because I have an agenda. mq double dot and m dot q dot are the same thing, right? The only thing happening here is that k is 1/2 q dot transpose mq dot with respect to q. The only thing that has q is the in matrix, right? So you can get these by partial differential here. If I write it this way, you see m appear as a constant, as a coefficient of q double dot, which is acceleration. The rest of these have q dot and q dot multiplication of q dots, right? So we can separate these and write this as a b q dot equals our centrifugal forces, right? So we are going toward that goal to bring this to the form of our generalized equation of motion. Now, what I'm missing there is m. This is mq. So these are just reviews on how of what we are doing here. And then I'm bringing g to the other side because this is the external force, and you can't take gravity to the external force from Earth to our robot. It's not because of how the robot is configured or how it's moving. There's always gravity applied to it, right? So we keep the gravity force and our external force on one side and keep everything else on the other side. Now what, so far so good. We know this, we knew this before. Now how the explicit form shows itself. Now that we brought everything, we made everything about our q dot and the velocities, but and the partial differential of m respect to q's, we can say that if we, for every single link, if we wrote the kinetic energy, because we're taking care of potential energy, we took it to the other side, right? Now we only have to deal with the kinetic energy of every link. If we wrote the kinetic energy of every link separately and added them together, we should get the same thing, right? It's the same idea. So this is what we had from previous slide. We also know that we can write the kinetic energy of every single link. Now, the link could have a linear velocity or an angular velocity, right? If I write that as generalized way and get the summation of all of that, I'll get something like that. One comes from the linear velocity, one from angular velocity. Now we also know the velocity, the linear velocity is jv dot, right? And we know that the angular velocity is j omega q dot of that link of end effector. Doesn't matter. Does this make sense? What is happening here? So look at some CI. Let's say that link I. All right. The velocity of that link is because of the velocity of all the links before it. It could be our end effector, or it could be any link that we decide we're going to calculate up to here. So now if you start walking from the first one, the second one, the third one, if you write all of this, at the end you will reach to your end effector, right? So if we replace these velocities with their counterpart, including the Jacobians, then mi, well, this is a fixed value. VCI transpose, so VCI is JVI Q dot, you get the transpose Q dot, transpose JVI transpose, and then CVI, this is JVI Q dot, and same thing for the omega I. Now, can we bring MI outside behind this? Because there's no fixed values, right? M is not going to change as you move. It's going to be fixed for that one link, right? So we can take that out. Can we take the Q dot T transpose and Q dot I? Do they change as you move for every link? So if your link 3, if your third joint is a revolution and you call it theta 3, it always stays at theta 3, right? It's not changing. So I'm gonna do this. I'm gonna sandwich this summation between Q dot T transpose and Q dot. So they would stay at the end, will be multiplied by. Now, if we look at the original generalized form, for these two to be equal, what should happen? 1/2 is equal, this is equal, this is equal. M must be this for them to be equal. So that is where the explicit form comes in. It basically says that if you know the Jacobian linear and angular Jacobian, and you know what is the mass of that link, you don't have to write the equation of motion separately for the link. You just use them and add them together. That becomes your mass matrix. Why this is useful? In our MQ double dot plus B equal to tau minus G, we need to find MQ, right? That is the MQ. So we are finding the mass matrix from the Jacobians, which mass matrix basically tells us how the velocity of each thing impacts the system configuration, right? So now, this here is important. We said that we will walk through every link. So let's say we are at link I. So we can write PC1 for the position of the first link, the position of second link, and then the position of last link. Every single link after that will get 0. We place 0 because we want the dimension of our matrices to be the same, so we can add them, right? Because we are summing them, they need to be the same dimension, but if they don't have value, we just put 0. So it does not impact our simulation. We just like make sure that we can apply the mathematical operation to them. Does that make sense what happened there? Yes. So this is the velocity of joints appearing after this CI. So the joints that we haven't walked through them, we'll give them 0. All the ones that we walked through them, we put their values in there. So basically our end effector starts from 1 link, then becomes a 2 link, then becomes a 3 link, 4 link, all the way to the end effector. And for J omega, you've already done it, right? Depending on if it is a prismatic or angular motion, it's either 0, 0, 0 or some value that becomes a unit vector. So 0, 0, 1 or 0, 1, 0, depending on the configuration of your robot. Then you have your mass matrix. For that so we have the mass matrix, we know Q double dot is, so we have the first part. We have tau minus G also. Now we have to find the centripetal and Coriolis terms. This is a little bit big part because we have lots of Q dot times Q dot or Q dot square in it. So there is a method called Christoffel coefficient, but how did we get there is a big article, but what I'm going to do is I'm going to introduce you how to calculate these coefficients from, all right? If we follow the first slide, we said that this term, we called it V. We just said this is called V. So M dot Q dot, we said M dot is piecewise, right? Oh, this is, so if you think this is a 2x2 example, the 2x2 robot, a 2-link robot with the M matrix. So M dot 1, 1, M dot 1, 2, M dot 1, 2, M dot 2, 2. Now, how to calculate this M dot 1, 1? M dot 1, 1 is the first element. You want to know how much each joint impact that mass, right? So think about it. If you have 2 links, if the first joint moves, you have 2 mass connected to that, right? If you're moving the second joint, only one of the masses will impact. So this mass matrix is going to tell us how these are all related. So to find M dot 1, 1, we basically are checking the relationship, the impact of joint 1 on that and the impact of joint 2 on that mass. And M111 is M11 respect to your Q1. So you want to know how changes in your Q1, your joint 1, impact that link with mass 1. Once you calculated that, for the second part, for the second one, so that is this guy. For this second matrix, all you have to do is find MQ1 and MQ2, which are element-wise, and to find it, you will find that's the same thing, the partial differential of that link's mass with respect to different joints. All right. Now, since these are all symmetric, so mass matrix is a positive definite symmetric. So you will have a lot of them that are the same. N112, N112, they will be the same number. So you don't have to actually calculate everything. You calculate in half of them. All right. And for symmetric, the other half is the same. Now, okay, confusing enough. Let's say we found all of this. If you rearrange, you'll see that we will have a matrix multiplied by Q dot 1 squared and a matrix multiplied by Q dot 1, Q dot 2. So these are the 2 different velocity combinations. So you always have to check if there are 0, why does it make sense for them? Let's see if I can give you an example for that. Yeah, let me finish this and I'll give you an example on mass matrix. What do I mean one link impacts the other link's motion? So this is Christoffel's symbol, comes from the previous slide. So basically there is a pattern going on here. Like if you look at here, you see the pattern between them. So now if this is when you have 2 joints, what if you had 6? So this pattern will go through. So you don't have to actually even do this. All you have to remember or have next to you is this. you will have two matrices, C, that is multiplied by the square of joint velocities, and then E, which is multiplied by the joint velocities that are not from the same joint, multiplied by each other. Now, this one is your centrifugal force. This is your Coriolis. So this is your Coriolis matrix, and this is for centrifugal force matrix. So these are product of velocities. This is a square of velocities. So all you have to do, you have to find what are these B111 and what is the B112, for example, here. And these are, yes, similar B's. So you actually count them one time and then you create your matrices. How do we find these B subscripts? That is the equation, Eijk. All right, so you have one equation, this, to create all the elements in your C matrix and your B matrix. And then you put it in the formula. Now, what does Mij mean? The first two is the elements of the mass matrix. The third one is the variable that you're getting that partial differential with respect to that. So you write, you see that Mij plus Mikj minus Mjki. So you're basically rotating them, all right? And you create your B, the element for your B and C matrix. So for mass matrix, you use Jacobian. For centrifugal and Coriolis, thank you. You will use Christoffel symbols. And we had G on the other side, right? For G, you can also use Jacobian. It will be basically velocity Jacobian, linear velocity Jacobian times mg. MGH, right? And tau is external forces. So you have the equation of motion. Question, can we use the other method that we learned, find out all the kinetic energy, all the potential energy, and just follow Euler-Lagrange and put it in the equation of motion form? Yes, you can. Why would we use this method? If you already calculate Jacobian for your model of the robot, you already have mass matrix and the G. All you have to do, put it in the Christoffel to find the third one. Then you have your equation of motion. So this is an optional method if you want to use when your robot becomes a multi-link. So the links are too many that calculating all of those. So you did that for, was it for 3? The one that we did the other day, 2. 1 rotation and 1 prismatic, right? Remember how long you have to write. Now imagine that's a 6 or 5 link robot. It will be really big. Using this method, the explicit method, it's shorter and more organized and allows for less error. Otherwise, either way, either method for equation of motion are correct. Now, do you think you can use this method for your previous example and get the equation of motion? Yeah. You can try, right? Let's try that. So, all the things you need to find is Jacobians, so you can find mass matrix and G, and then the Christoffel. So start from mass matrix because it's easier, it's just a Jacobian. And then we go to the other one. We have time. What time is it? First of all, tell me what's the dimension of your mass matrix? 2 by 2. So can I say with high confidence that my mass matrix is going to be M11, M12, M21, M22. Right? I can say that, okay? So we are finding equation of motion using explicit form. I'm gonna say my Q is going to be theta 1 and D2. The best way here is to use direct equilibrium. To be, if you have the position, you can get the. I kind of wrote it so you can fill them in. Patrick, can you tell me how to populate JV1?
So the first column is going to be one, and the second one will be zero actually.
Zero. Why? Because we are on link one, right? So we're trying to find the Jacobian impact of velocity on link one. So we find that, and then the second column is zero. Okay, so how about JV2?
Same thing.
Does that make sense? So as we go, our robot kind of is expanding. The first one was just one link. Now JV2 is the row with two links, so it has two variables. So let's populate JV1. Oh, sine 1. This is being L1 cosine 1, 0. This is 0, 0, 0. This negative 3. This one. Okay, Adam, how do we populate J omega 1?
It will be the axis will be 0, 0, 1, and then go to the next one.
So we don't do the second one. And then how about J omega 2?
Maybe the same thing.
Okay, what's the difference though?
Well, you don't care if it's math.
So this is prismatic. So this happens to be the same. So we are looking at our robot. When we are at our first link, we only have one joint, right? So J omega is only 0, 0, 1. The way that joint is rotating is the axis of that. And anything after that, we don't care. We put 0, but we know there's a placeholder. We should be able to do our matrix multiplication operation. Now, when we move to the second joint, now our first joint is, it has angular velocity, the same axis 0, 0, 1. Happen to be here, second joint is prismatic. So the element for prismatic for that becomes 0, 0, 0. So even though they're the same, the reason for them is different. Now, we populated that. So we populated these two, we populated that. All they have to do is write M. So M1, some number, JV transpose, we have JV1, JV, J omega transpose, IC1, if you remember, we had it in our previous example, right? Here we are rotating about z-axis, so we only need the inertia about z-axis. And basically from here, you just put everything together and you write this in matrix form. That's your mass matrix. Right? Instead of, if you remember, doing all of those calculations to get your mass matrix, you're basically plugging and playing your mass matrix. Does anybody have the mass matrix to read it for me? So your total mass matrix will be, if you add all of them, where IZZ1 came from IC1, M2D2 squared plus IZZ2, 0, 0, M2. You compare, this should be similar as your other example. Makes sense. But here you can see better how the velocity, joint velocities impact your mass matrix. If someone asks you, what does mass matrix represent? What does it represent? In an equation of motion? Okay, that's what the second part of it. What does mass matrix in an equation of motion represent? You see how the velocities are distributed and configured in your model, right? How does it impact the motion? The inertia, the mass, and the velocity. Now, you should be able to use this example to find the mass matrix of CP15. Was that the last CP? The two prismatic robot. John, bring that up. Bring that example up from your last CP. Find the mass matrix for that. Using this method, explicit form. There you go. Very simple. Right? All you have to find is JV, right? What's your J omega? 0. So now knowing this form could have helped you a lot in actually writing that.
Yeah.
Can somebody tell me what they find? So J omega 1 is 0, J omega 2 is 0, right? So we don't have that second part. So your M matrix is M1, JV1 transpose JV plus M2, JV2 transpose JV2. Now, what is JV1 and JV2? Yes.
So JV1 will be 0, 0, 1. And JV2 will be 0, 1, 1.
So, even though this is a 2D, when you are talking about so this, I saw that in your exam too. So your Jacobian will be 3 by the number of your joints. So it wouldn't be 2 by. You always have in X direction, Y direction, Z direction. The 0, 0, 1, and your second column 0, 0, 0, right? Because you're at the first joint. Now, when you move to the second joint, you'll have 0, 0, 1, and then, so if this is your Z0, X, and Y, then you're in X direction, right? That's 1, 0, 0. So you have your JV1 and JV2, the only thing you need to do is transpose, put them together right now. I will post a solution this way as well, so you can see it. Now, we have a quick 5 minutes. I'm going to go back and show you how easy the Christoffel could be. It looked very complicated when I was showing you all the equations, but do you remember to find those B elements? What did you need to know? Like, what was each B element composed of? M, right? Something that you do with M. You just found all the elements of your M matrix. So you actually have them. You just have to get some partial differential with respect to your variables. So we have our M11, which is this term. This is M12, M2, M21, right? And this is M22. So M12 equal to M21 equal to 0. M22 is M2. Now, the Christoffel tells you that your Bijk is 1/2 Mijk plus Mikj minus Mjki. Now, these only mean Mijk is the partial of Mij with respect to k. All right. Now, starting from your first one, so M111, M112, so that's it, right? So you can go M111 and M112. We already did that. So this means you have to find M11 with respect to your first Q1, which is your theta 1. And this is M11 with respect to your second one, which is D2. Right? Now, since we know M12 and M21 are 0, we don't have to calculate them. It's 0. The only thing that we will have left is M221, M222. Well, D2. Everything else is 0. So you only have to calculate 4 things and then just create that matrix. Just plug it in. Right? So this method, once you find the Jacobian, everything else just plug and play. And for the gravity, you already have the Jacobian. It's just plug it in. All right. So this is supposed to be easier if you had the Jacobian of your molecules. And highly suggested when you have a complicated one. If there are different names and you have like different ones. All right. If I gave you PA some point that you need to calculate the equation of motion, choose whatever way. Go online, find the equation of motion. I don't care. Because at that point, how you solve it is different. All right. So For every system that is a two-link robot, the equation of motion are out there. You don't have to even calculate. But it is good to know how it was drawn. All right? Okay. All right, that's about it. So I'll go to solution, and then on Wednesday, it's gonna be very something to do.
My brain will hurt. My brain will hurt.
Pause this.